Hello students, this lecture is about solving mechanical energy problems. Now we've learned about mechanical energy and we've learned about the three different forms of mechanical energy: gravitational potential energy, kinetic energy, and elastic potential energy. And now we're going to learn how to solve problems using them so that we can actually know how much energy in joules we have in a particular object. So our objectives for this lesson are to interpret known information from a problem. We're going to learn how to do that. And you should also be able to solve for unknown information using these three equations that we're about to learn. The GPE equation, so for gravitational potential energy, the kinetic energy equation, the KE equation, and the elastic potential energy, or EPE equation. Okay, let's take some notes. The first form of energy we're going to talk about is gravitational potential energy, or GPE. And we've already learned in a previous lecture that GPE depends on an object's height. The higher up an object is, then the more energy it has, because it has a greater ability to cause change, which is what energy is, a greater ability to cause change from a greater height. So it makes sense that the GPE of an object is going to depend on its height. There's a couple other things that GPE depends on as well, though. It's also going to depend on the mass of the object. Now, the mass means how much stuff there is in an object, and we measure that in kilograms. And this sort of makes sense as well, because if you think about it, a large object placed at a height is going to have more ability to cause change than a smaller object placed at that same height. So the mass of the object, how much stuff there is in the object, is going to matter. We're also going to talk about the acceleration due to gravity. And this is basically how fast the force of gravity of the Earth is going to be speeding us up. How much does the Earth, or wherever we are, want to speed us up where we are? And we just symbolize that by the letter G, small g. Here's an equation that ties these three things together. It's actually pretty straightforward. GPE, or the amount of gravitational potential energy that I have, is the product of mass, acceleration due to gravity, and the height of the object. So if I know these three properties of the object, I can just multiply them together and end up with the GPE. Let's remember to use standard units. So height, we always want to measure in meters. Mass, we always want to measure in kilograms. And the acceleration due to gravity, we measure in units of meters per second squared. And we're actually going to learn why that is a little bit later on in the year. Let's talk about the kinetic energy of an object. And if you recall from a previous lecture, the kinetic energy of an object is the energy that it has stored in its motion. Objects in motion have the ability to cause change. Therefore, they have energy. How much energy? Now we're going to be able to calculate it out. We're going to say that the KE of an object depends on the square of the object's velocity. So if I know how fast this object is going, I need to square it, and that's going to be a term in my equation. And the mass of the object. So think about a small car moving along at 30 miles per hour and a very large bus moving along at 30 miles per hour. Even though they have the same speed, they're going the same speed, definitely the bus has more ability to cause change than the car because it's bigger. There's more stuff there. It can do a lot more damage if it ran into something, let's say. So here's my kinetic energy equation. KE, the kinetic energy of an object, equals 1/2 times the mass times the square of the velocity. Don't forget this square. This can be really important, and it's going to give you a very different result if you forget to leave it on. Okay, and our third form of energy, of mechanical energy, is called elastic potential energy, which we have talked about in previous lectures as the energy of stretching, of squeezing, of tension, compression, deformation, bending. Anytime you change the shape of an object, well, most of the time that you change the shape of an object, you're going to get some kind of elastic potential energy involved. And this equation, EP equals 1/2 kx squared, it looks a lot like this equation up here. We're just going to put different terms into it. This K is called the spring constant, or sometimes it's called the coefficient of elasticity or elasticity coefficient. All it is a measure of how difficult it is to stretch this object, or how difficult it is to squeeze it. Does it really want to keep its current shape, or is it pretty easy to squish and squeeze and stretch? That's what K measures. So a higher K, if this number is higher, that means it's harder to change its shape. It's harder to stretch and squeeze. This X is what's called the displacement, and that is basically how far away we have stretched a certain point. And that's going to make a little bit more sense when we do an example later. So just hang on to that idea of what this X means, and we'll practice in just a moment. And now I actually need to go back up here and add something here to my notes, because I talked about the acceleration due to gravity as little g. We actually want to give that a number. This is what we call a constant for at least most of the problems that we're going to be dealing with in intro physics. G represents the acceleration due to gravity at Earth's surface. And for most applications in our class, that's going to be equal to 9.8 meters per second squared. We'll learn why that is at a later point in this year, but for now we can just call it, this is how much the Earth's gravity wants me to be speeding up all the time near the Earth. 9.8 is very close to 10. For problems in this class, we can just round, and we're going to call that 10 meters per second squared. Okay, so we are approximately equal to 10 in almost all problems that we will be doing. Okay, let's try some examples. So here I have a boulder with a mass of 50 kilograms, and it's at rest on a hill at a height of 7 meters. What is its gravitational potential energy? So let's start by drawing a diagram, which is always a good start to a physics problem. I'm going to write on the side here, known. These are where this is where I'm going to put all the things that I know about this scenario. I know that I have a boulder on a hill, so I'm going to draw my boulder there. And I know several other things about this object. If we scroll up to see what I've been told, I can also draw those things over here on my notes. I know that the height of this boulder is 7 meters. It is 7 meters high. I also know that the mass of this boulder is 50 kilograms. That's how much stuff is in that object. These are going to be useful pieces of information when I actually want to solve the problem. There's another important piece of information in this example, and that is the words at rest. At rest means that it's standing still. It's not going to matter too much for this problem because we're just asked to find the gravitational potential energy, but I do want to point out that these words, even though they're not providing us a number, they actually do give us something very important about the problem. That the velocity, how fast the object is moving, is 0. Okay, so anytime we see the words at rest, we want to start to practice writing down that the velocity is 0, at least where it says that the object is at rest. Now, I'm asked to find the gravitational potential energy of this object. I'm going to look at my notes and write down the relationship between gravitational potential energy, mass, acceleration due to gravity, and height. This formula gives me that relationship. It says that GPE equals mgh. And now, when I want to solve this equation, I can just plug in what I know. I know that the mass is 50 kilograms. I know that g, the acceleration due to gravity, in this class we can approximate as 10. And the height of this object is 7 meters off the ground. If I multiply all these together, let's see, 50 times 10 is 500. Times 7, I'm going to simplify that. And 500 times 7 is 3,500. Now, in physics, a number by itself as a solution doesn't really mean anything. I cannot just leave my answer as a number. It has to have some kind of physical meaning, or it's not really physics. So I need to put units on this number. The units of energy are joules, which I represent with a J. So now I've gone through the solution of my problem. Let's recap what we did. We read the problem, we looked for important information, we summarized our important information on a diagram and clearly labeled what we know about this object. We wrote down the relevant relationship between the variables that we know. An equation is just a statement of a relationship, and we wrote it down to remind ourselves. And then we plugged in what we knew. We know the mass is 50 kilograms. The acceleration due to gravity, we're just calling a constant of 10 as an approximation. The height of this object is 7 meters off the ground. And I can just multiply that all out to get 3,500 joules. That is how much energy this boulder has. Let's try another example. I would like you to pause the video and use the same problem-solving approach to solving example 2. Okay, let's try this problem. Same way. I'm going to write my knowns in a very clear spot so that I know what I know. I'm going to draw this kitten as a dot. You'll find that in physics problems we tend to be a little bit lazy with our drawings. We make the simplest drawing that gives us the relevant information. So I'm just going to show the kitten as a dot, and here's the ground, and I'm going to draw an arrow to show that it's running. I know a few things about this kitten. I know that its mass is 1 kilogram. And I know that it is running at 3 meters per second. Its velocity is 3 meters per second. So I've set up my notes. And now I'm going to look back in my notes and say, okay, this is a kinetic energy problem. What relationships do I have between kinetic energy and other properties of an object? Well, I know that the kinetic energy is equal to 1/2 times the mass times the square of the velocity. So I'm going to write down my equation, my statement of relationship right there to help me plug in what I know. Now let's plug in what we know. 1/2 is just 1/2. The mass of this kitten is 1. Its velocity is 3. And I want to make sure that I don't forget the square. Okay? 3 squared is 9. 1/2 times 1 is just 1/2. 1/2 times 9 is 4.5. And again, the units of energy are joules. It doesn't matter what kind of energy it is, if it's GPE, if it's KE, if it's thermal energy, elastic potential energy, if it's electrical energy, any form of energy we're going to measure in joules. So let's do a quick recap of this problem. I read over the information that I have. I summarized my known information in a neat diagram, also labeling the variables that I know with their units. And then I wrote down a statement of the relationship, the equation, K equals 1/2 mv squared. I plugged in what I know, all my known values, and I solved for the final solution of 4.5 joules of energy. And now we can make a comparison. Only 4.5 joules of energy for this tiny kitten, moving along at 3 meters per second. Notice that this 50 kilogram boulder at a height of 7 meters has 3,500 joules of energy. So even though this boulder isn't even moving, it's not doing anything, it has a lot more potential to cause change than the kitten. And why does it have that? Its mass is much bigger, and it's at a great height. Okay, let's try a third example. Once again, let's pause the video and try and solve this problem using the problem-solving methods that we've discussed. Okay, let's see how we did. This one is a little bit more challenging because there's more information. Let's see how we can do this problem. Step one, as always, I'm going to write my knowns. And the first thing I do is I draw a diagram. I've got a bird flying at some height above the ground. I know a few things about this bird. I know that its mass is 3 kilograms. So I'm going to write that down. Mass of the bird is 3 kg. It is flying at a certain height, and that height above the ground is 10 meters. So I know that this height right here is 10 meters. I'm writing down the value, the variable, and the units. H equals 10 meters. And one more thing I know about this bird, it is flying at a speed. It has some motion of 4 meters per second. So I want to include that as well. Four meters per second. So now I've summarized my information on a diagram. I've labeled it. Let's make a statement about what we need to find. Well, from a previous lecture, I know that the mechanical energy of something, which is what I'm looking for, the total mechanical energy, I know that it's the sum of all my forms of mechanical energy. I know that it is equal to GPE plus KE plus EPE. Okay? The total mechanical energy is the sum of my gravitational potential energy, my kinetic energy, and my elastic potential energy. In this case, it doesn't seem like this bird is being stretched or squeezed, at least to any significant amount. So we're probably going to ignore elastic potential energy for this particular problem. There's no stretching, no squeezing going on, and in any case, I don't have the information to find it. Let's try looking at two separate forms of energy. The first is the GPE. I'm going to write down my relationship for GPE equals mgh. And I also know that the kinetic energy of this object is equal to 1/2 mv squared. I'm going to need to use both of these equations to solve for how much total mechanical energy I have, because this bird has both. It has GPE because it's up at a height of 10 meters, and it also has KE. It has kinetic energy because it's in motion at a velocity of 4 meters per second. So let's solve these separately and see what we get. My GPE is equal to mgh. So I know my mass is 3 kilograms. Little g is 10 meters per second. That's the acceleration due to gravity. And I'm at a height of 10 meters. Let's see. 10 times 10 is 100. Times 3 is 300. So this bird has 300 joules of GPE, 300 joules of gravitational potential energy. Let's use blue to solve for the kinetic energy. 1/2 mv squared. Let's plug in 1/2 times 3 kilograms, that is the mass of the bird, and I know it's moving at 4 meters per second, and I'm going to square that value. I'm going to square that value. Now, 4 squared is 16. Half of 3 is 1.5. So I have 1.5 times 16, and that is going to be 24. joules. So we have two forms of energy in this bird. We have 300 joules of gravitational potential energy because the bird is flying up at a height. And we also have 24 joules of kinetic energy because the bird is in motion. But I'm not done yet. I'm not done yet because the problem has asked me to find the bird's total mechanical energy. This is what I'm trying to find. What is the bird's total mechanical energy? So I need to put these together in a final step that the total mechanical energy is just going to be the GPE plus the KE. I need to add them together. So that's 300 plus 24, which is 324 joules of total mechanical energy. Let's do a quick recap. I read through my problem. I made a neat diagram that was labeled with what I know. I wrote down the relationships that matter in this particular problem, and then I solved one step at a time. I knew that this bird had both height and speed, so it must have both gravitational potential energy and kinetic energy. At the very end, I wanted to find the total mechanical energy, so I just added up all the forms of mechanical energy that are involved, the GPE plus the KE, to get a total of 324 joules. Okay, let's try a fourth example. In this case, Mr. Ratnayaka's Aston Martin has a mass of 1,875 kilograms, and I'm asking you how much kinetic energy does it have when it's moving at 65 meters per second. That's something around 130, 140 miles per hour. So try this problem, pause the video, and see if you can do it. Okay, as you may have guessed, this is a kinetic energy problem. So just as usual, I'm going to set up my knowns. Here are my knowns. Let's give myself a road. My car is moving along my road at 65 meters per second. That is my velocity. And I also know something else about this car, that the mass of the car is 1,875 kilograms. What am I looking for? I'm looking for the kinetic energy of the vehicle. So let's write down our kinetic energy equation. KE equals 1/2 mv squared. That is my relationship between the variables. So let's plug in what we know, just as usual. 1/2 is 1/2. Mass is 1,875 kilograms, and my velocity is 65 meters per second, and I have to add the squared. Don't forget the squared, or you'll end up with a very, very different answer. So 65 squared is 4,225. And let's see, 1/2 of 1875 is 937.5. And if I multiply those together, I end up with a large number, much larger than what we've seen so far. It's 3,960,937.5 joules. I put the units on at the end there. That is a very large number compared to what we've seen. Almost 4 million joules of energy. Why does it have so much energy compared to the other examples that we have seen? Notice that it has a very large mass compared to the other examples that we've seen. And also it's moving very fast. 65 meters per second, again, is around 130, 140-ish miles per hour. So it's both quite massive and very fast. So we do end up with a lot of energy. Last example, example number 5. So I have a spring with a spring constant of 0.25. is stretched half a meter from its normal position. How much elastic potential energy is now stored in the spring? Pause the video and see if you can do it. Okay, let's see if we can draw this out. Here are my knowns. And the way I want to draw a spring, I can draw kind of a spring like this. And what I'm going to say is that it is stretched out some distance. If I've stretched this spring out, it's storing elastic potential energy in the spring. So I'm gonna write my knowns. K, 0.25. That's going to be the elasticity of the spring. How tough is it to pull that spring? And I know that it has been moved half a meter from its normal resting position. And then this becomes a pretty straightforward use of the elastic potential energy equation. I know that EPE equals 1/2 K x squared. I'm going to plug in what I know. 1/2 times 0.25 times 0.5 squared. Well, let's see. 0.5 squared is 0.25. And I have 0.25 again over here. So let me close my parentheses with a 1/2. And I can multiply all three of those together. And that is actually a very small number this time. We have 0.031 joules. And that is the amount of energy that has been stored in this spring. It's a very small number. Why is it a small number? Because this is not a very stiff spring. It has a fairly low spring constant. And also I haven't taken it very far from its initial position. It's only half a meter, 0.5 meters from its normal position. But when I lay out my knowns on a diagram, I recognize the relationship that I need to use, and I can plug in and solve to get the answer. So let's go back to our objectives for this lesson. You should be able to interpret known information from a problem. So that was where I listed my knowns on a clear and neat diagram on the side. And you should be able to solve for unknown information using the GPE equation, the KE equation, and the EPE equation. And it's okay if this seems very fast right now. We're going to do a lot more practice in class and a few activities to see how these forms of energy relate to each other.